All right, I'm going to try to make these videos reasonably short. We'll see how it goes. So we're starting chapter 3, which can be a little abstract. Is the thing, I think there's several reasons why this is the case. One, it's the definitions for things like vector spaces are kind of abstract, and it's not clear for quite a while how they're connected to applications or differential equations. They're connected in the sense that differential equations can be interpreted quite nicely in terms of linear algebra. That derivatives and integrals are linear transformations on vector spaces of functions, and the eigenvectors of those linear transformations form important subspaces. So it's a little easier to talk about differential equations if you have the language of linear algebra. But let's start 3.1. Let's start with vector spaces. Vector spaces are admittedly abstract structures, and this is typical math stuff. Mathematicians noticed common properties in lots of different situations, came up with a list of the requirements of what does a collection need to be a vector space. And that list of properties is going to seem kind of, vague or abstract or non-specific. And adding to the problem is we start this with a pretty good idea of what we think vectors are. They're little pointy arrows. We lost lots of points in physics for forgetting to draw an arrow over a letter to indicate it was a vector, not a scalar. Our physics TAs, yelled at us if we confused vectors and scalars. We were told again and again that vectors are things with directions and magnitude. That's not true. I mean, it is true, but there are vectors that don't have direction, and there are vectors that don't have magnitude. Those are additional structures. So this definition isn't going to illuminate the ideas that you already have. So that being said, let's jump into it and start practicing. Sorry, it's early. Here's the start of it. So you have a bunch of things. It could be a collection of polynomials, a collection of functions, it could be a collection of matrices. The collection needs to be closed under addition. That means however you're adding these things together, if you add two of them, you should get something that you already have in the collection. It's called closure. It's really common in mathematics. It's not something we often talk about in science and engineering. Vector spaces also have an associated field of scalars. All that means is there's a particular bucket of numbers. For us, it'll be the real numbers, though there are plenty of applications where they're complex. And that we're allowed to multiply vectors by numbers. And if we do that, we end up with vectors that we already have. So the process of adding vectors and scaling them keeps us inside the same collection. And there'll be examples in the future that indicate where these things go awry. Now, on page 99 to 100 of your textbook, there are 8 properties that form the definition of a vector space. These first two, they're never going to bother us. This is the sort of thing that's hard to imagine a collection breaking. There are collections, which is why mathematicians write this stuff down. These are the places that we're likely to find something that goes awry. So a collection has to have a 0 element if it's going to be a vector space. If it doesn't, then the collection isn't a vector space. It also has to have an inverse for every element. So if there's some u in V, then there needs to be a minus u. Quite often it will be a minus u. So that when you add them together, you get the 0 element, which is another reason you need to have the 0 element in your vector space, so that you can add these two things together and end up with something that you already have. And then these last 4, again, are the sorts of properties that are hard to imagine not having in a collection. So not all of these are equally important for us. Let's dive into an example before I ask you to try some out on top of that. So here's an example. Let's take all the 2x2 matrices. So all the 2x2 matrices with real entries, they form a vector space. So the first two properties, pretty clear. Not going to spend any time there. Adding matrices is commutative. It's also associative. There is a zero element in that collection. It's just the matrix with all zeros. If you add any 2 by 2 matrix to this matrix, nothing happens. For any 2 by 2 matrix, A, B, C, D, there is another 2 by 2 matrix, minus A, minus B, minus C, minus D, that if you add those two together, you get the 0, 0, 0, 0 matrix. So those two are taken care of, and then so are these. If you multiply a sum of two matrices, it's the same as multiplying them individually, and so on and so forth. So these are vectors. 2 by 2 matrices are vectors. This will get a little confusing, because 2 by 2 matrices will also be linear transformations on vectors. We've already talked about that a little bit. It'll turn out that linear transformations are also vectors. A lot of things are vectors. In fact, scalars are vectors. Yeah, if you really want to irritate your physics TA, ordinary numbers form a one-dimensional vector space. Think about it. Any two real numbers can be added and you get another real number. Any real number has an additive inverse. You can multiply real numbers by real numbers and end up with something you already have, and so on and so forth. So the number 7 is a vector. Just saying. All right. I'm going to, I'll try another example. Something that fails. So here's an example of a collection. Degree 2 polynomial. So remember, degree is the highest power. With positive coefficients. So this is a specific collection, quadratic functions with positive coefficients. A, B, and C are positive. So this fails to be a vector space because there's not an additive inverse, for example. So if you have the quadratic 2t squared plus 3t plus 8, the additive inverse minus 2t squared minus 3t minus 8 is not in this collection. It's not in there. So that fails. Also, 0t squared plus 0t plus 0 is also not part of this because 0 is not positive. It's neither positive nor negative. So that's an example of something that fails. Now, it's not because they're polynomials. The collection of all, degree 2 I meant to have here, polynomials is a vector space. Any two quadratic functions you can add and get another quadratic. Any quadratic function has an additive inverse. The 0 function is a quadratic function. So this collection fails because of the restriction of positive coefficients. All right, I'm going to pause there and allow you to answer some questions and opt into the discussion if you want to. Again, notice there is a discussion for the entire lesson here that starts right after this video.